So here's my talk. I'm gonna get into some of the fundamentals of non-uniform sampling. We've already seen some beautiful overview work on how spectral processing incorporates Fourier transform and what happens when we start to non-uniformly sample our data sets. And then Jeff showed a number of different reconstruction algorithms and how they can work with that non-uniformly sampled data. So this talk is designed to kind of go back to some considerations into how you would form your sample schedule. And this will hopefully arm you with some guides for the tutorial session I'll do after our lunch break. And that'll set you up for the processing tutorials we do later this afternoon with Frank. So let's start off with some basic terminology. If we're going to talk about a 3D experiment, we have two indirect dimensions and our one direct dimension. Here we're seeing T1 and T2. These are our indirect dimensions. And at each one of those points, we collect our FIDs along T3. We refer to this as our sample space. And each of the points in that sample space, courtesy of David Donahoe, we've got a cute name for it. It's called an indel, an indirect element. So this is like a pixel being a picture element in your monitor, or a voxel being a volume element if you were doing a continuum mechanics simulation. You can see here that our points are on grid, and we've got uniform dwell times along T1 and T2. And this constitutes uniform sampling. This is something we're all familiar with. Non-uniform sampling is simply not collecting FIDs at some of those indels. So if we were to consider uniform sampling and use quadrature detection, if we had a single dimension, this would be our direct dimension, we'd have one FID. And if we put that at about 5 seconds for collection time and relaxation, we can step our way through increasing number of indirect dimensions. Here we've added an indirect dimension and it's got 128 points. With quadrature detection, we now have 2 FIDs per indel, and we're looking at a 20-minute experiment. And as we continue to increase this, you'll see rather large growth in the experiment time and the number of FIDs. Now keep in mind, this is coming with pretty conservative choices for the number of points we're going to include along our additional indirect dimensions. We're not going to get the full resolution that our fancy new expensive high field magnet promises. So here we are looking at an experiment that's going to require something like 4 months to collect, and it's going to be suboptimal. So we need to do better than that. So let's do a quick comparison and see if non-uniform sampling here can come to the rescue. So as I just mentioned, uniformly sampled experiments can be prohibitively long. Non-uniformly sampled experiments can be arbitrarily short. When it comes to spectral processing, we've already seen the Fourier transform today. That's pretty straightforward. We understand how to use that. And as Jeff highlighted, with non-uniformly sampled data, there are a variety of reconstruction techniques that are available, and many of them can be a little bit complicated potentially to configure. The Fourier transform is a linear function. We know how it handles input data, signal, and noise. The notion of signal to noise ratio makes sense. With nonlinear reconstructions that come from non-uniformly sampled data, that becomes a bit more complicated. In terms of sampling artifacts, for uniform sampling, we might be tempted to say there are none, but there still are some underlying assumptions that we're making, especially if we're working on grid. And when it comes to non-uniform sampling, certainly there can be a very wide range of sampling-induced artifacts. Now, common standards. With uniform sampling, yeah, given a grid size, a Nyquist sample space, you've got one way to uniformly sample it, and you've got one way to use the Fourier transform. So it's pretty straightforward to use traditional FT-NMR data processing. With non-uniform sampling, quite simply, no, there are not common standards. There are tried and true approaches and methods that have been published and people routinely go back and use, but they're not necessarily based on full optimizations or full quantitative analysis of all the options. So in terms of a community opinion, at the end of the day, uniform sampling is well characterized, pretty straightforward. And with non-uniform sampling, we're still standing here making the claim, you can collect less data, get a better experiment, and some people view that as black magic. So that's the introduction to non-uniform sampling. And now we're going to step through a couple of different topics here and see how these properties of non-uniformly sampled data relate. So we'll go through sensitivity, resolution, sampling-induced artifacts, randomization, and then at the end, a quick plug for NUScon. So let's start off with sensitivity and resolution. We've already seen a couple variations of this slide today, but we'll still touch on the topic again. So if we have two decaying sinusoids that are close in frequency, here we have a blue signal and a black signal. If we sample this only through the short evolution times, we're going to have a very high level of sensitivity because the intensity of this signal is very large at these low evolution times. But we're going to have a very low resolution. We can barely resolve the difference between that black and blue decaying sinusoid pair. At the very tail here, we can just barely start to see that difference. So in contrast, if we were to sample out to longer evolution times, well, our sensitivity has decayed. We're now picking up less intense signal, but we now have a higher resolution. So let's formalize that a little bit. And we can turn to this beautiful paper from David Robniak and company. And we're going to talk about something called the intrinsic signal to noise ratio. So I just showed you those sinusoids on the previous slide, and you can envision a signal envelope wrapped around those sinusoids as we saw those signals decay. If we were to take the area under that signal envelope out to a maximum evolution time of T max, we just integrate, and that'll tell us the total amount of signal intensity that we've captured. Similarly, the amount of noise that we get out of that signal is going to scale as the square root of the maximum evolution time. So if we take the ratio of these two quantities and evaluate that integral, we get this nice clean formula here that tells us the signal to noise ratio as a function of our maximum evolution time for uniformly sampled data. Now what David has done is he's taken a synthetic peak that's been injected on top of experimental noise, and he's taken that data and truncated it at different maximum evolution times as shown on the horizontal axis. For each of those truncated data sets, it's been processed with the FT, and then it's been scaled so that the RMSD of the noise that you see down here towards the baseline has an RMSD value of 1. Therefore, the intensity of the peak that you recover is the signal to noise ratio that we can read off the vertical axis. And those peaks superimpose beautifully on the theoretical result, this curve, which comes from the equation up here at the top. And what we can also point out here, and Jeff mentioned this in passing in his talk, is that we see a maximum signal to noise ratio that occurs right around 1.26 times T2. So now let's turn to resolution and see what sort of quantitative observations we can make there. So in this case, David's injected two synthetic peaks, and he's varying the spacing between those peaks from 1.2 line widths all the way up to 3 line widths. And that synthetic data set is then once again truncated at different maximum evolution times from 1T2 to 2T2 out to 3T2. And what you can see here is that when the peak pair is widely spaced, this top row of our figure, it's very easy to resolve those peaks even with a truncated data set only going out to T2. As the pair of peaks get closer and closer and closer together, you now have to sample out to longer and longer maximum evolution times to resolve them. In the theoretical limit, if you had no noise, you could resolve peaks down to a single line width of separation if you went out to pi times T2. So if we take those two observations that we've just seen, if we're using uniformly sampled data and processing, anything beyond 1.26 times T2 is going to lower our sensitivity, but we need to go all the way out to pi times T2 to improve our resolution. So these two observations give us this forced trade-off between sensitivity and resolution when we're using uniform sampling. So with non-uniform sampling, we'd like to be able to include some long evolution times, but bias most of our samples to the short evolution times. And then we can utilize some advanced sparse reconstruction techniques to handle that sparse data. Ultimately, what we're aiming to do is deploy non-uniform sampling in a way that lets us improve both sensitivity and resolution while reducing experiment time. And in order to meet these guidelines over here of including some long evolution times, but mostly sampling short evolution times, there are a lot of ways to do that. So we're going to try to constrain ourselves to pick approaches that meet these objectives while minimizing the sampling-induced artifacts. So if we want to be able to do that, we're going to need a way to quantify those sampling-induced artifacts. So let's start off here with an overview of a non-uniformly sampled experiment and ask the question, how does that NUS experiment relate to the equivalent uniformly sampled experiment? So here we have a uniformly sampled time domain data set representation for a 3D experiment, and here's a 2D plane. Each of these colored dots represents some FID data. If we were to take the Fourier transform of that, here's our uniformly sampled spectrum. We can define a sample schedule where, excuse me, where the black dots indicate FIDs that are going to be sampled and the blank spaces indicate FIDs that will be skipped. Numerically, this can be represented as a matrix of ones and zeros, so we can convert this to something as a numerical mask. That mask we can use on our uniformly sampled time data to throw away the FIDs that are not included in our sample schedule. So here is our NUS time data. And as we saw in earlier presentations, if we go into that non-uniform time data and fill in zeros for FIDs that are not collected, and this is not something we would do in a reconstruction, but for the purposes of this exercise, if we fill in those zeros, we once again have a uniformly sampled data set. Then we can apply the Fourier transform and we get this NUS spectrum over here. So the broad question that I posed at the top of this slide is pretty much, how does the uniform spectrum and the non-uniform spectrum here, how do they relate to each other? So we can take our sample schedule of ones and zeros, and if we take the Fourier transform of that, we get something called the point spread function. This point spread function, through a convolution operation with the uniformly sampled spectrum, exactly gives us the NUS spectrum that we see here on the end. And we'll take a closer look at this point spread function in just a minute. But I do want to make it absolutely clear that I'm not suggesting people collect NUS data and zero fill it in order to take a DFT. This DFT convolution relationship that we see here is for illustrative purposes only, and it helps us make a comparison between two different sampling schemes and the nature of the sampling artifacts that a given sampling scheme might introduce. In practice, you would take this NUS time data and one of the various non-Fourier reconstruction methods that Jeff already spoke about, and you would use that to do your reconstruction, and in the end, hopefully get a spectrum that looks very much like the uniformly sampled spectrum up here, if not better. So here's the DFT-Convolution Theorem that I just showed you by picture on the previous slide. And the basic idea is we have our time domain data T. If we take the Fourier transform of that, we get our uniformly sampled spectrum. If we take our time domain data T and we subsample it with our sample schedule S, take the Fourier transform, that gives us our NUS spectrum. The connection between these two is given by the point spread function and this convolution operator that we see right here. So let's take a look at that point spread function. For those of you that might have more of a background using microscopy or other imaging systems, the point spread function is simply telling us what's the response of our imaging system to a single point source of light, a single delta peak of light. How does our imaging system capture it? And that point spread function then shows us the physical imperfections or biases in our imaging system. So in this example here, here's our point spread function. A single point source of light is presented to this system, but it's recorded as this blurred vertical disk here. And if this is our real image that we're trying to capture with our imaging system, when we look at this image, the point spread function would be convolved with that, and what we would actually recover is something that looks like this. So you can see the two features that were in that image, and each of them have been smeared by that point spread function. So what the convolution is doing for us is it's giving us a weighted sum that's produced by sweeping this point spread function, by smearing it all over that real image. Now, in the case of NMR, when we take a look at a point spread function of a sampling schedule, this is what we will end up getting. We'll have a single strong peak right in the center at the zero frequency position, and the intensity of this peak is going to scale with the number of points in our FID, with the number of points in our sample schedule. And then all around that peak, we will see sampling-induced artifacts. If we have a very clean sample schedule, we won't see much in the way of artifacts. If we have a poor sample schedule that introduces lots of artifacts, we're going to see non-zero values around that zero frequency component. One of the things we can do to evaluate the intensity of the artifacts that would be introduced by such a sample schedule is to look at the ratio between the intensity of the peak and the largest value that we see away from the peak in this point spread function. We refer to that as the side lobe. And the ratio between the peak to side lobe is a single quantitative measure that will tell us the intensity of the artifacts that we can expect to see. So let's take these concepts and combine them and take a look at a toy problem here where we're going to look at convolution with a bad point spread function. So in the top, we've got a toy problem spectrum with two peaks, number 1 and number 2, each with these shoulders next to them. And here's our bad point spread function. Here's our zero frequency component right in the middle. And then instead of having all zero values around it, we have some large artifacts in our point spread function out here at the extremes. So when we perform our convolution operation, what we get are scaled versions of this point spread function shifted across our spectrum. And this is how the convolution operator works. It takes scaled and shifted versions of that one function and sweeps it across the other. And the convolution is the resulting summation of all those scaled and shifted point spread functions. When we add that up, this is the resulting spectrum we would get if this is our point spread function and this is our master data set. So if we were to go and inspect this resulting spectrum, we find that peak number 1 is recovered correctly. Because of sampling-induced artifacts, we see an artifact next to peak 2 that has a larger intensity than peak 2. So we'll find peak 2, but we're going to misassign its position by 1 grid point over here. And out at the wings, we have 2 very large sampling-induced artifacts that are false positives. So this little example here shows how a poor point spread function coming from a poor selection of a sample schedule can really complicate the analysis and interpretation of even the most simple data sets. So let's just take a quick look at some sample schedules and PSFs just to give you some visuals to go with some of those theoretical concepts. So here we're looking at Poisson gap sampling, random sampling, and envelope matched sampling, which biases the FID selection to the decay rate of the signal envelope. And these are examples taken at 30% sample coverage. Right next to it, you can see the point spread function for each of those. And then we're showing point spread functions at even more reduced sample coverages of 10% and 5%. And you can start to see some ridge artifacts that show up around those zero frequency components in some of these sample schedules. Of course, the random sampling has one single small red pixel there in the center with pretty much no features around it, as we would expect. So here is another slate of sample schedules you can take a look at, things that have been used for various purposes in the literature, and you can see all kinds of wacky patterns and shapes and artifacts that show up in these point spread functions. And here's one final one, and here's the beat matched sampling. This ought to look pretty familiar to that machine learning solution that Jeff shared with us earlier. And I'll call your attention to this one down here in the bottom called triangle sampling. This is not something that somebody would employ, but it is the strongest bias you can impose by pushing all of your FIDs to those lowest evolution time points. I'm going to come back to this in just a minute. So to summarize what we've looked at so far in terms of sensitivity, uniform sampling beyond 1.26 times T2, that's going to lower our sensitivity. Resolution for uniform sampling out to pi times T2, that's necessary to get the maximum resolution. But with NUS, we're trying to strike a balance where we want to include some long evolution times, bias most of our samples to those short evolution times. We've taken a look at how sampling-induced artifacts can be quantified. We have a couple metrics that can be deployed in advance. We can look at a point spread function and the peak to side lobe ratio to get an understanding of the magnitude and the nature of the sampling-induced artifacts that might be introduced. So the next question we want to ask here is, can randomization and dimensionality be used to suppress our NUS artifacts? So at one extreme, we've got random sampling. There are absolutely no constraints. FIDs are selected from across the entire sample space. At the other extreme, we have triangle sampling, where everything is compressed to that lower corner that I just showed you. It turns out that most reasonable schedules are going to be somewhere in between. So let's see what happens in that in-between region. And to do so, we'll introduce a toy problem here, where we're going to intentionally create very large sampling artifacts. And then we're going to play around with randomization and dimensionality, and we're going to see if we can suppress those artifacts. So we'll introduce this idea of uniform undersampling. So here we have an indirect dimension T1, and we're sampling 1 out of every 8 points along that dimension. And if we repeat that across a second indirect dimension T2, we get a sample schedule that looks like this. So let's start with the same approach again. We're sampling 1 out of every 8 points along T1. We repeat that along T2, but this time we're going to randomly slide those columns up and down to different positions. So now we no longer have coherence between those columns as we go along T2. And we refer to these two approaches as the fixed offset on the left and the random offset on the right. And that's going to be the basis for our toy problem. So here is a purely random sample schedule. And here is the corresponding point spread function. In this case, here's our zero frequency component right in the middle. We don't really have any artifacts around it. So the peak to side lobe ratio is a very, very, very large number here. Now let's take a look at that fixed offset approach that I just showed on the previous slide. In this case, our point spread function is going to have our zero frequency component, but then it's going to be flanked by 7 perfectly aliased peaks. These will be regularly spaced and have the exact same intensity as that true peak right in the center. So what this corresponds to is every feature in our spectrum collected using this sample schedule would show up 8 times. In this case, the peak to side lobe ratio equals 1, and this is essentially the worst type of situation we could create. And now here we are with the random offset, which is using the same 1 out of every 8 FIDs being selected along T1, but all we've done is slide those columns up and down. And in this case, what we see in our point spread function is that these aliased peaks that you saw here with the red circles in panel B are being squashed and distributed along F2. And the one true peak remains in the middle. So we get a very, very effective suppression of our sampling-induced artifacts. And through a full survey of various parameters that define these types of sample schedules, we can get a nice, clean quantitative result where we get an equation that looks like this. So the peak to side lobe ratio is going to scale as the number of points along each of our indirect dimensions, or M, that maximum increment, raised to alpha times D, where D is the number of indirect dimensions, and alpha is a scaling factor that we have. So where does alpha come from? It turns out for our fixed offset case, where we introduced the worst sampling-induced artifacts, what we observe is that alpha equals 0. A 0 exponent results in a peak to side lobe ratio value of 1. This is where we have our largest artifacts. Our purely random sampling results in this equation holding for an alpha value approaching a value of 1. And for the random offset case that we play with, what we find here is that the alpha value approaches D minus 1 over D. So think about that for a second. We've got uniform undersampling along T1. We're taking 1 out of every 8 sample points in this case. In every single additional indirect dimension, we're including randomization. So D minus 1 over D is simply the number of dimensions that include randomization out of the total number of indirect dimensions. So the more indirect dimensions we have, the more effectively the randomization across those indirect dimensions mix together and recover us in going from an alpha value that's close to 0 back up to an alpha value that's close to 1. And over here on the side of this figure, you'll see that alpha value as the number of indirect dimensions increases. So this shows us how effectively we can suppress those sampling-induced artifacts. And you'll see that with only one indirect dimension, we're unable to suppress those artifacts. But once we introduce that additional indirect dimension that has randomization, we now have a value of 1/2, then 2/3, 3/4, 4/5. So we continue to approach that value of 1. And what's interesting here is that the biggest improvement that we see comes from that very first jump. We get marginally less and less and less as we go, meaning that even for modest experiments of only 1 or 2 indirect dimensions, really paying attention to the use of randomization is going to help you suppress those sampling-induced artifacts. So the conclusions from that portion of the talk, we've seen that NUS is an effective way for simultaneous improvement of both sensitivity and resolution. We've looked at point spread functions and peak to side lobe ratios as a way to understand the characteristics of NUS artifacts before we collect an experiment. And we've taken a look at how dimensionality and randomization can be effectively used to introduce some decoherence and reduce our sampling-induced artifacts. So what I'll close with is kind of the obvious open question. So what's the best way to approach NUS? And Jeff hinted at this already, and I'll bring it up here, and that's NUScon. That's where NUScon comes into play. So here's the graphical representation of a traditional uniformly sampled experiment. Here's your uniform data. You apply the DFT, you get a spectrum, you peak pick, you get a peak table, you go off and you do your quantitative analysis. When it comes to non-uniform sampling, well, first you have to select which FIDs are you going to collect and which ones are you going to skip. Then with your sparse data, you have to choose a sample reconstruction algorithm. Then once you get your resulting spectra, that's going to have certain nonlinearities in it, and you have to figure out how to interpret the peaks and peak shapes that you see. Peak picking that becomes a challenge. And then of course, with your resulting peak table, you have to figure out the best way to interpret those results. So the overall challenge here is really what are the best practices for designing and processing NUS experiments. And NUScon has been making some strides towards answering those questions. We do so by posing some challenge questions to the community, and we have them build their own reconstruction scripts, which they submit as their entries. And we apply those reconstruction scripts to data that has been injected with synthetic peaks. And we see how well the contestant scripts are able to recover those synthetic peaks. Here's a little bit more information about NUScon. You can go to the website, nuscon.org, to see some info there. You can also sign up on the NMR Box website if you'd like to get onto the email list for that and get more information about the challenges that'll come out in 2020 for the next contest. A huge thank you here to David and Miriam Donahoe for sponsorship of this, as well as unheard of cash prizes in the NMR world to really incentivize the community to rally around this and form some best practices. This is the workflow that I already mentioned, and that wraps things up here. All right, thank you all for your attention through that presentation. If there are any questions, I'd be happy to take them. All right, Rajan.
Oh, hi, Adam. Thank you. It's a wonderful talk. So if I conceptually understand this correctly, it looks like if there is a proper full randomized filter is applied for, then that's probably the ideal case, correct? So it gives you the point spread function, which has the best ratio of the peak to no artifact, peak to artifact.
Yeah, that's a great question. So if you go with random sampling, you're going to end up with the minimum of sampling induced artifacts.
Right.
But if you're looking at a decaying time signal, you're not going to have great sensitivity because the earlier time points have more signal intensity than the longer evolution time points.
So the point here is coming to this point of accuracy with which we can reproduce a NUS sample spectrum. So I mean, so there is this question like, yeah, at a cost of sensitivity, I think as a spectroscopist, I'd be probably more worried if I have false positives, is it not? If I, so that looks like conceptually, it inexorably pulls me towards going more random distribution of the filter you apply for to generate the NUS scheme will be a better bet. Yeah, I know there is some kind of a trade-off about the S by N. So is there like some kind of a cutoff where we say, beyond which if you go to this level of randomness, you are almost sure that the peaks you reproduce are going to be real ones, and you're good to go. So you can definitely don't go below this level of randomness, even if you gain sensitivity. So is there anything like that in your understanding? Is that such a cutoff? Or
Yeah,
it's a kind of
that's a great question. So the machinery that you'd need to really answer that question for the specific system you'd be looking at would be the IROC method that Jeff discussed. So if we were to take all of the true signals that exist in your spectrum and look at a histogram of their intensities, and then look at a histogram of all of the noise in your spectrum and look at those intensities, very rarely are you going to have a spectrum where those two distributions are completely disjoint. In other words, you're not going to have a single threshold where all the noise is below it and all the signal is above it.
Okay.
In that case, with the overlap, then you're going to be forced into making a trade-off where when you set your threshold, you're either going to be missing some true peaks, but picking up additional.
Okay, makes sense. Yeah. Yeah. Thank you.
You can't even reach it there.
Andy, you got a question? Or that may be left up from a previous question. Okay, I don't think Andy is there. So if there are no other questions.
No, Adam, I just couldn't find the unmute button. Sorry.
Go ahead, Andy.
So it's somewhat of a comment and a question. I know Dave Robniak worked on sampling schemes and was trying to look at, the whole quartile topic that we didn't go into, and that's okay, on grid, off grid, et cetera, et cetera. But where does fifth sampling scheme fall into this random and so exponentially weighted random type schemes?
That is a fantastic and wonderfully leading question. So when I do my tutorial this afternoon, I have quantile sampling built into NUStool, and we're going to step our way through it.
Okay, cool. Thank you.
You bet.